So Beer's law is a law that relates a solution's concentration to its absorptivity, or its absorbance, meaning how much light of certain wavelengths it absorbs. And the equation is written as A, which is the actual absorbance of light, which will have to be measured by what's called a spectrophotometer. The absorbance of light equals epsilon, which is called the molar absorptivity, which is a constant for each substance, times B, which is the path length, meaning the length that the light has to pass through the solution, times C, which is the molar concentration. So, if we think about this, since molar absorptivity is a constant for each different substance, and we could control the experiment where the path length of light is always the same, essentially that makes molar absorptivity and path length constants, which means they can be written out of this equation, and it can be stated that the absorbance is directly proportional to the concentration of the solution. So let's look at an example. So on the left we have a 0.2 molar solution, which is a light red. And on the right we have one that's 5 times as concentrated. It's a 1.0 molar solution. And you can tell just by looking that the 1.0 molar solution is a darker, deeper red than the 0.2 molar solution. If we were to shine light through this 1.0 molar solution, since it's more concentrated and the solution is darker, it would absorb more light, allowing less to pass through. If we use a spectrophotometer, we can capture that light that comes out, and that will let us know how much was actually absorbed by the solution. Again, since this one on the left is of a lighter shade, it will absorb less of the light, meaning it will have a lower absorbance. So by relating these absorbances, we can determine the concentration of these solutions. So, in order to do this, we need what's called a spectrophotometer, which looks just like this up here on the left. Nothing too fancy. You will pour, or pipette rather, your solution into what's called a cuvette. C-U-V-E-T-T-E, a cuvette. And it's kind of hard to tell from this picture, but you'll notice that the sides of the cuvette are different. This side right here is smooth, whereas the side that's kind of turned right here has these ridges along the side. It's important that you line the cuvette up the correct way into the spectrophotometer. So down here on this spectrophotometer you can see this white arrow. That's the direction of the light as the machine shines the light through. You want that light to go through this smooth side, that way there's no accidental absorbance. If you were to put this ridged side in, those ridges might absorb some of that light, giving you an incorrect absorbance. Also, when you handle this cuvette, it's important that you only touch these sides with the ridges, as those are the sides that are not being measured. If you were to touch the smooth side, the oils in your finger might deposit onto the smooth side, which will cause more light to be absorbed, and you'll get a false reading. So here we have some absorbance data. We have shined a light using a spectrophotometer through 4 different solutions with known concentrations, 0.2, 0.3, 0.4, and 0.5 molar, and we have their respective absorbances. So imagine we had an unknown solution, and we filled a cuvette with this solution, and we shined our spectrophotometer through it. And let's say that our spectrophotometer gave us an absorbance reading of 0.30. Now, from this data, we can conclude that the concentration of this unknown solution must be between 0.2 and 0.3 because its absorbance is between 0.27 and 0.41. Now, this doesn't get us as close as we might hope, but if you were to plot this data and place a regression curve onto it, which I'm just going to sketch for you real quickly. If we plotted this data of concentration versus absorbance, we would see that as the concentration goes up, so does the absorbance, And a regression curve is nothing more than a line of best fit. Forgive my terrible not straight line. We could then use a calculator and its programmable regression function to determine exactly with an absorbance of 0.30 where this would fall on this line. However, in class our spectrophotometers are programmed to simply do this for us, so we don't have to go through the calculations. We would just have to plug in 0.30 onto our lab equipment, and that would tell us our molar concentration, which would be somewhere in the ballpark of 0.22 in this case. But it's this logic of absorbance increasing as concentration increases that is the basis behind Beer's law and allows you to make judgments on concentration of unknown solutions based off their absorbances.